All right, so today's date is Tuesday, November 19th, 2019. Today we're talking about the symmetry of 2D shapes. And before I talk about this lesson, let's take a look at our unit guide. So if I come back over here, notice that our unit guide for Unit 2 transformations, we are at its end, which means today is 2-14, tomorrow's a quiz, and the day after that is the test. So we're finishing up this unit before Thanksgiving. All right, so let's go ahead and learn our last lesson for the unit. Our objective today is to determine types of symmetry, find magnitudes of rotational symmetry, and to create symmetries. So, reflective symmetry is the first type of symmetry I'm going to be talking about. The second of the two is rotational symmetry. Reflective symmetry is as it sounds. It's a shape that can be folded in halves, and both halves are congruent. Congruent. So I think that's pretty self-explanatory. Let's go ahead and take a look at an example. So here we have a quadrilateral. This is one of the points of the quadrilateral, and we need to know that it's reflective symmetry over x plus 4. So x plus 4 is, of course, this line with a y-intercept of 4, and this line y equals negative x that goes through the origin has this negative slope. So it has reflective symmetry over both of these lines, which means I need to make that quadrilateral using these properties. So the way that you do that is just reflecting over this line. It's a line of reflection. So you can kind of count diagonally. I think on the slopes for Kite Academy, they're always either going to be 1 or -1. So you just take the opposite of that. Technically, it's the opposite reciprocal, but the reciprocal of 1 is 1. So you go diagonal like this, and you count, okay, I'm going 1 diagonal and another 1 diagonal, which means I have gone 2 diagonals, so 1, 2, and there is my new vertice. Again, you're doing the same thing down here, so going diagonally. Again, the reason I can go diagonally is because the slope is opposite reciprocal, so I'm going down, 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 down. So I'm going 4 of these diagonals. Sometimes you might go 3.5. I'm going 4, and then through this origin, I'm going 1, 2, 3, 4 diagonals, and I get a point down here. And it's the same process again over this line. I can either go out diagonally this way or diagonally this way. It doesn't matter. I'm going to get the same answer either way. I think it's easier to find this diagonal because it's only 2 diagonal squares and 1, 2 diagonal squares, and I have the vertices of my shape. So usually you have to actually make lines on Kite Academy, so I will do the same thing. Let's go use yellow. So those are the lines, and I guess I'm gonna have to make this one and move it down, and there is our shape, and it has reflective symmetry over each of those. And you can see that if those were a crease on a piece of paper and I folded over, it would match up perfectly. I mean, the right half or the upper right half is congruent to the bottom left half using our definition of reflective symmetry. And one thing that I should talk about too is the second part of the question. So draw and define the quadrilateral defined above. So we have drawn it, so check, but defining it we have not done. So what shape does that look like? Technically, it's a rectangle. So the answer here is rectangle. It has many other words for it too. It's not just a rectangle, because if you're a rectangle, you are other things as well. And just a bit of review, since these are both parallel to one another and these are also parallel to one another, this is also called a parallelogram. Parallelogram. If this segment and this segment were the same, along with all these, if all 4 of these are the same, it's kind of like a squished square. In this case, it would actually be the square. But if the angles were not exactly the same, that would be a rhombus. So think of a rhombus as a squished square. What else do we have here? You could have a kite, depending on how your lines of reflection go. Again, a kite, you can draw it off to the side, just trying to make sure that we know all of our basic quadrilaterals as a review. This is a kite. It does have one line of reflection, and it's right there. It doesn't have a line of reflection right there because this piece is not congruent to that bottom piece. There are quite a few different problems, but they're all kind of in this realm of just figure out how many lines of reflective symmetry you have, etc., etc. So let's talk about rotational symmetry now. When the shape rotates by a magnitude of rotational symmetry, that's what it's called. You can see it down here. It's magnitudes of rotational symmetry. Then the original shape maps to itself. So what do I mean by that? First, let's write down magnitude. A magnitude of rotational symmetry. All right, so here we have a hexagon. I know it's a hexagon because 1, 2, 3, 4, 5, 6 sides and 6 angles as well, 6 vertices. So if I were to rotate this by 1/6 of a rotation, by this amount of rotation, then this piece would become this piece would become this piece. They would match up exactly. This line segment will be this line segment, which means that the shape is mapping onto itself. It'll look exactly the same as if I never rotated it, as long as I have rotational symmetry and I'm actually rotating it by the magnitude of that rotational symmetry. So we have to figure out how much I can rotate by. So if I rotate by 1/6 of a full rotation, I can write this down here. So a full rotation is 360 degrees, and I can make the note over here. That's a full rotation. Full rotation. And then I'm going to divide this, and I said it's divisible by 6 because this is a 6-sided shape. Sometimes it'll only be divisible by 1. It has 360-degree rotational symmetry. And by the way, that's always an answer. D is always an answer. If you have 360 degrees, that is always going to be a magnitude of rotational symmetry because it rotates onto itself, no matter the weirdness of the shape. But this one is regular, which means that it can rotate 1/6. And because there are 6 sides, there are 6 ways to rotate this. I'm going to divide a full rotation by the number of sides. So I can say down here, this is the number of sides, which is not always true. Just because it has 6 sides doesn't mean that I'm rotating by, or I'm dividing by 6. You just kind of have to figure out, well, how many times can I rotate this before it goes back to itself? In this case, it's 6. Feel like I'm beating a dead horse. Let's go ahead and do that. So I know that if I was just doing 36 divided by 6, that's 6. Add the 0 back on, and I have 60. So it has 60 degrees of for its magnitude of rotation. So B is definitely an answer. But notice if I multiply 60 by 2, I'm rotating twice of that, and it's still going to be the same shape. So I can do 60 times 2, I can do 60 times 3, 60 times 4, etc., until you get down to 360, and at that point you're just kind of repeating yourself. So notice that 60 times 4 is 240. Again, if you don't believe me, 6 times 4, 24, add on the 0. Which means C is also an answer because it is a multiple of 60. And I'll write that as well. Multiple of 60. 60 is kind of like the base magnitude of rotational symmetry, and then from there you can just keep multiplying by some whole number, by some integer. Again, this doesn't cover even half of the types of problems. They're all kind of mixed up like this, but at least you now know how rotational symmetry works and how reflective symmetry works. Good luck on Khan Academy. Hopefully I will be back at school tomorrow. I am feeling slightly better. All right, good luck, guys.